Welcome to all of you. Now we discuss Unit 2 2020 Biomathematics Semester 5 CBCS Mathematics Honors University of Calcutta. Unit 2 Question 4a. Find the steady states of the following preparator system dx dt equal to x bracket 1 minus x by 13 minus xy by x plus 10 divided equal to y bracket x by x plus 10 minus 3 by 5. Investigate their stability. For steady state x star comma y star dx dt equal to 0 equal to dy dt for this x star y star. So if we put x star and y star in place of x y, we get this dx dt equal to 0 at this point x star y star. So this equal to 0, and from second equation we get this equal to 0. From the first equation, taking common x star, we get this. So either x star equal to 0 or this quantity is equal to 0. And from the second equation, either y star equal to 0 or this quantity equal to 0. Solving these, when x star equal to 0, then y star equal to 0, so we get trivial equilibrium point E naught, this equal to 0 comma 0, and x star y star are all non-negative quantities for feasibility of biomathematics. And so when we solving this from this second equation of this second equation, this x star equal to 13, and if we put x star equal to 13 here, so we get y star equal to 0. And so solving this, we get two steady states, E naught 0 comma 0 and E1 13 comma 0. Now to find Jacobian matrix, let f xy is this function and gxy is this function, right hand side of this second equation, and partial derivative find the partial derivatives of the functions f and g, del x of f, del y of f, del x of g, del y of g. Then Jacobian matrix J is given by this 2 by 2 matrix, and this next stability analysis for this point E naught trivial steady state 0 comma 0 origin. So put x equal to 0, y equal to 0 here, so we get the Jacobian matrix for this point 0 comma 0 is we get this. Obviously the diagonal elements, the eigenvalues of this system, then 1 and minus 3 by 5 are eigenvalues. This here 1 is positive and minus 3 by 5 negative, so 0 0 is a saddle point, that is an unstable steady state. Next, for E1 steady state 13 comma 0, we get x equal to 13 and y equal to 0 in this matrix J. We get this is the upper triangular matrix, and these eigenvalues are this minus 1 and minus 4 by 115, and so both are negatives. So steady state 13 comma 0 is a stable node. Next question 4b. Write a short note on transcritical bifurcation and Hopf bifurcation. Transcritical bifurcation, it is a particular type of local bifurcation in which a fixed point exists for all values of the parameter and is never destroyed. Here the fixed point interchanges stability with another fixed point as the parameter is varied. Consider an example, this ordinary differential equation dt of x, this is equal to mu x minus x square, mu is parameter, and for fixed point x star dx dt at this point x star equal to 0, so we get mu x star minus x star square equal to 0, so we get two steady fixed points x1 star equal to 0 and x2 star equal to mu. Let fx mu, the function is the mu x minus x square, and then del x of f equal to mu minus 2x. The del x of f at this point x1 star equal to 0 equal to mu, and del x of f at this point x2 star equal to mu, equal to minus mu. Now put here x2 star mu x equal to x star equal to mu, so we get minus mu. Put here this mu minus 2 mu, so minus mu. Case 1, when mu is less than 0, then this x1 star is stable because this fx0 is negative, this minus mu negative, and x2 star equal to mu is unstable because this quantity is positive. And when mu greater than 0, x1 star is unstable because fx0 is greater than 0, and x2 star equal to mu is stable because this fx mu less than 0. Phase portrait for this is the x-axis, this is the dx dt. Actually dx dt means this curve, for this curve mu x minus x square, mu x minus x square. So put certain value of mu, say mu equal to minus 2 here. So for this curve, this minus 2x minus x square, y equal to this, and draw this curve this, and this curve cuts the x-axis at this point mu, at this point 0, and this is the minus mu for this. So this unstable, this arrow is that away from this, from the right hand side, because this dx dt is positive, here dx dt is negative in this direction, so this negative side arrow and this the positive side arrow, so both arrows away from this point. So and this for this point towards this point, so this stable point. And for when mu equal to 0, that is fxy equal to mu equal to 0, so fxy equal to minus x square, so y equal to minus x square. Draw this graph y equal to minus x square, this graph. And for this dx dt is negative, so arrow in this negative direction, and here dx dt is also negative, so negative direction. So this arrow towards from the right hand side towards this point origin, and away from the origin this arrow. So this part is this side is stable and this side is unstable, so it is called semi-stable. Origin is semi-stable. And for mu greater than 0, so if we put mu greater than 0, say mu equal to 1, 1, that is x minus x square, y equal to x minus x square, and then we can draw easily this graph this. And for this mu and this 0, and this mu is stable and this 0 is unstable when mu greater than 0. And the transcritical bifurcation diagram for this, this axis is mu axis and this is the vertical axis is x star. So this bifurcation occurs at this point mu equal to 0, when mu is negative. So mu negative, this origin is stable, so this mu x star equal to 0 is stable, and mu x star equal to mu unstable, so dotted line, so this unstable. And after when mu is greater than 0, after origin in the right hand side, this steady state x star equal to 0 is unstable, this unstable, and this x star equal to mu is stable. So this fixed point x star equal to 0 is stable for mu less than 0, and unstable when mu greater than 0. And other fixed point x star equal to mu, unstable for mu less than 0 and stable for mu greater than 0. So this point origin is the bifurcation point. Actually this is called the supercritical transcritical bifurcation, supercritical transcritical bifurcation diagram. This is the next Hopf bifurcation. It is a mathematical concept of nonlinear dynamical system where fixed point losses stability, a parameter is varied, leading to the emergence of a limit cycle or periodic orbit. Consider an example. The system dt of x equal to mu x plus y minus x bracket x square plus y square, and dt of y equal to minus x plus mu y minus y bracket x square plus y square. In polar coordinates, if we put x equal to r cos theta, y equal to r sin theta, and r greater than 0, this system 1 reduces to this dt of r equal to r bracket mu minus r square, and dt theta equal to minus 1. and the only critical point is r star equal to 0, that is the origin. Then and since d3 dt is negative, so trajectories move clockwise sense about the origin. Case 1, when mu less than equal to 0, then dt of r equal to r mu minus r square is negative. As r is positive, mu is negative, hence there is no closed orbit and all trajectories approach origin as t tends to plus infinity. So the critical point 0, 0 is a stable focus. So this dt of r is less than 0, dt r less than 0, no closed orbit and all trajectories approach 0, 0. For case 2, when mu greater than 0, then dt of r equal to this, and this is less than 0 for root mu less than r less than infinity, and this greater than 0 for 0 less than r less than root mu. So the origin 0, 0 is a unstable focus for this, and there is a stable limit cycle for r equal to root mu as all trajectories approach the limit cycle for root mu less than r less than infinity. Actually, the phase portrait of this when mu less than 0, this phase portrait is this clockwise sense towards this stable focus for mu equal to 0, and it's also stable focus, origin is stable focus. And when mu greater than 0, we get a limit cycle r equal to root mu. This is the limit cycle, and this is the origin critical point, this towards the trajectories approach towards this critical limit cycle. So this is the origin critical point, origin unstable steady state, and from outside this approach to this limit cycle, that is all trajectories. So actually this limit cycle is stable limit cycle, and this Hopf bifurcation for this is the mu axis, this is the y axis, vertical axis, and this is the x axis. Actually the three-dimensional diagram for this when mu less than 0, and we get a stable critical point, this origin critical point, stable critical point. And when mu greater than 0, this origin is the critical point origin is unstable. So this is the unstable critical point origin is unstable. This x star x y star is greater 0, 0, unstable critical point, because we get this. And then for mu greater than 0, we get a stable limit cycle, and so this is the stable limit cycle for this. Actually, if we draw this stable limit cycle is this. So this clearly the asymptotically stable critical point 0, 0 for mu less than 0 is bifurcated at mu equal to 0 into an unstable critical point 0, 0 and a stable limit cycle r equal to root mu for mu greater than 0. These limit cycles form a paraboloid. Actually, this is the paraboloid form. Actually, this is the paraboloid in the xy mu space for mu greater than 0. This is the Hopf bifurcation. Next question. Question 5. What do you mean by limit cycle for the nonlinear dynamical system? Show that the following dynamical system possesses a limit cycle x dot equal to y plus x bracket 1 minus x square minus y square, y dot equal to minus x plus y bracket 1 minus x square minus y square. Also study the nature of the trivial equilibrium point. Actually, what is the limit cycle? A closed path C of a nonlinear autonomous system. What is the meaning of autonomous? And when the system does not depend on explicitly on time t, then system is called autonomous. This is the nonlinear function dx dt equal to some function pxy, no t, explicitly does not depend on t, dy dt equal to q xy, which is approached spirally from either the inside or the outside by a non-closed path C1 of 1, either as t tends to infinity or t tends to minus infinity, is called a limit cycle of worm, and this is an isolated closed trajectory of worm. where PQ have continuous first order partial derivatives in a simply connected region in the domain of definition. Second part of this given system is this: x dot means dx dt and dy dot is dy dt, and corresponding linear system is x dot equal to y plus x and y dot equal to minus x plus y. And for the equilibrium point x star y star, so x dot equal to 0 equal to y dot for this point. So clearly x star and y star equal to 0 0 is the only trivial equilibrium point of the system and of the nonlinear of the equilibrium point of the system 2 as well as 3. System 2 nonlinear system and system 3 and linear corresponding linear system. From 2 we get this in matrix form: x dot y dot column matrix equal to 1 1 minus 1 1 1 1 minus 1 1. Coefficients of this coefficient matrix is this x y. So corresponding characteristic equation: 1 minus lambda 1 minus 1 1 minus lambda equal to determinant of this equal to 0. So we get lambda square minus twice lambda plus 2 equal to 0. So lambda equal to 1 plus minus I, and hence the eigenvalues are 1 plus minus I. Clearly the real part of this eigenvalue, this 1, is greater than 0. The trivial equilibrium point 0 0 is an unstable spiral point for both 2 and 3, linear and nonlinear, nonlinear and linear system, corresponding linear system, because real part of this eigenvalue is positive. Introducing the polar coordinates x equal to r cos theta, y equal to r sin theta, r is greater than 0, we can find this x dot plus y dot equal to r square bracket 1 minus r square, and r square equal to x square plus y square. So differentiating with respect to t, twice r dot equal to this, so r dot equal to this, hence r dot equal to r bracket 1 minus r square. Next, if we find x dot minus xy dot, after simplification put this value of x dot and y dot, we get this equal to r square. Now yx dot minus xy dot equal to y means r sin theta, and x dot means minus r sin theta theta dot, and x equal to minus r cos theta theta dot. So we get minus r square theta dot, and hence theta dot equal to minus 1. So the given system 2 reduces to, in polar coordinates, r dot equal to r bracket 1 minus r square and theta dot equal to minus 1. Let f r equal to r bracket 1 minus r square, then f dash r equal to 1 minus 3 r square. Now f r equal to 0 implies r equal to 0 and r equal to 1. So we get two steady states here. So f dash 0 is equal to 1 greater than 0, and f dash 1 equal to minus 2 less than 0. Clearly r star equal to 0 is an unstable steady state, and r star equal to 1 is a stable steady state. And for this, so if r equal to r bracket 1 minus r square, if we draw this r axis and this corresponding f r, this r dot, and then we draw this curve r into bracket 1 minus r square, and this point r star equal to 0 and r star equal to 1, and this is the unstable, and this r equal to 1 is stable. We observe that dr dt, actually dr dt is this curve, r dot is positive when between 0 less than r less than 1, in between this part r dot is positive, and when this equal to 0, when r equal to 1 and r dot equal to 0, and also r equal to 0, dr dt equal to 0, but for r equal to 0 we are not interested as the system collapsed at the origin, and this and the r dot negative for when r is greater than 1, this part negative part is. Thus the trajectory is inside r equal to 1. R equal to 1 means the circle x square plus y square equal to r square move out to r equal to 1 inside the circle, because inside the circle means this 0 less than r less than 1, r dot is greater than 0. So r dot is greater than 0, so this move out to r equal to 1, and trajectory outside r equal to 1, that means when r greater than 1, r dot is negative, so move into r equal to 1, and when trajectory r equal to 1 equal to 0, so this trajectory stay on this r equal to 1 circle. Since theta dot equal to -1, all trajectories move in clockwise at a constant rate. Since r dot equal to 0 and r equal to 1, so r equal to 1 is the periodic trajectory. Actually, we get this stable limit cycle r equal to 1. This is the limit cycle, this closed isolated trajectory. This is the limit cycle r equal to 1, x square plus y square equal to 1. And from the outside, when r is greater than 1, this approach toward this trajectory towards limit cycle, and this critical point 0 0 is also unstable critical point, because all trajectories moves away from this critical point and goes to the limit cycle r equal to 1. So nearly trajectories converge to r equal to 1, that is to the circle x square plus y square equal to 1 from both the inside and the outside. So the circle r equal to 1 is a stable limit cycle, but the trivial equilibrium point or this 0 0 is unstable. And next question 6, this is the reaction diffusion system. Actually, this is the out of syllabus in the new revised syllabus, and question 7 is also activator inhibitor system is also out of syllabus, so we avoid this discussion answer for these questions. Thank you for watching this video.